So this is problem 2-36, and it is on page, I'm not sure,
37.
37, thank you. Knowing that the tension in cable BC is 725 newtons, determine the resultant of the three forces exerted at point B of beam AB. So let me copy it. You can see what we're looking at. There's a wall, there's a beam, and there's a cable pulling on that beam. And that cable is what they're calling CB. There's A, back here at the wall. And they've told us that the tension in that cable is 725 newtons. So which way does that cable push or pull on B? Up and to the left, doesn't it? So there's certainly 725 newtons of force pulling up on B. But there are also two other forces. There is a 500 Newton force and a 780 Newton force acting down to the right, down to the left. And they've told us the angle by giving us triangles. So this is a 5, 12, 13 triangle. If you're familiar with those, 5 squared plus 12 squared is 169, which is 13 squared. On the other side, the other force, 500 force, they've told us that this is a 3, 4, 5 triangle. And I really like problems like this because most students will think of sines and cosines and they'll try to use these numbers to get the angle. Well, guess what? We don't need the angle. We can solve this problem without using the angle at all because here's something really important. I want you to learn this. When you have a 500 Newton force like this, and you want to know what, and let's just call this force P, okay? And you want to know Py and Px, that makes a triangle, that 540 defines a triangle that is similar to the geometry triangle, the 5, 4, 3 triangle. Now maybe what you know is something about geometry that's given here, and essentially they've given you an angle in an odd way. Okay? But often what happens is that you need to break up a force like this 725 Newton force into components based on geometry. So what they gave us for this 725 Newton force rather than a 453 is the fact that CB has a horizontal distance of 840 millimeters and that the length of CB is 1,160 millimeters. So just as these two triangles are similar to one another, so we can calculate Py and Px scaling this based on this, we'll be able to do something similar here. Let's start here and then I'll show you what I mean. So Py, if these two are similar triangles, how would I calculate the magnitude of Py? Well, I would realize that Py, this distance, over this distance, is similar to, in other words, is equal to 4 over 5, right? Because they're similar triangles. In the same way, Px over P would be equal to what? You tell me.
3 over 5.
3 over 5. So in other words, Px is P times 3/5. So if we take 500 and plug it in, that's easy, that's 300 newtons, isn't it? So Px is 300 newtons. What is Py equal to then?
400.
400. So this side's 400 newtons, and this side is 300 newtons. Okay. So that breaks up this 500 Newton force into horizontal and vertical components. We can play the same game over here. Let's pause on that for just a second. Let's play this game instead. The geometry defines a triangle that looks like this. And we can figure out this side, right? How would we figure out this side? Wouldn't it be isn't that it? 1160 squared minus 840 squared? Do that for me, please. And tell me what the side length is on this triangle. Obviously there's your millimeters, but who really cares? Why do I say I don't care? Because I'm going to take ratios later and the millimeters drops off anyway.
That right side is 800.
800?
Yeah.
So they gave us nice round numbers to make sure this came out well, right? So The force that we want to break up, let me do this, maybe this will help, is a 725 Newton force. You see how it is similar, the geometry triangle? I could have made it bigger, I could have made it smaller, whatever, it doesn't matter, it just fits better here. So I made it smaller. So how are you going to calculate the length of this side? Well, all you have to do is scale it. So basically, what do you want to call this side? Can we call it BY? And this side BX, is that okay with you guys? So BY, and we'll call this B. BY over B, this side over the hypotenuse, is equal to what in terms of the geometry triangle?
About 800 over 725.
Not over 725.
This is over B, right?
This side over here is BY over B. That's the black triangle. This side over here is the geometry triangle. 800 over what?
Oh, 1160.
Good. See how the units have to cancel? So we're using similar triangles here. Okay. So what that tells us then is that BY is equal to B multiplied by 800 divided by 1160. Or in other words, since B is 725 newtons multiplied by 800 over 1160, that tells us what BY is. So calculate it for me. 725 times 800 over 1160 is what?
500.
It's 500? Okay. Again, they gave us nice round numbers. Gives you a warm, fuzzy feeling when things work out right. Okay. How about BX? Why don't you guys take a minute, see if you can figure out the magnitude of BX. All the triangles you need are right there. Give it a shot. You can talk to the person next to you if you're not sure.
He set up a proportion.
Yeah, again, we can try and
You can be loud, it's okay.
So,
Record your voice for posterity on YouTube, right?
Yeah,
would be equal to 840 over 1160.
when we have B, we have BX, so then we should just take that over and multiply it. So it's 25 times the
Yeah.
11, so what was the original relationship? So
Well, look at what it's in proportion to. It's in proportion to the 840.
Yeah.
Right? So it'd be 840 over 1160 equals
Yeah.
725 over B.
You mean the, BX over 725 is 725.
Yeah.
Okay, so it means 725 times, 840 over 1160?
No, it would be B of X over B right, because B is
I missed your step where you got
I think Connor was right.
725? That was given.
Yeah.
Over B and
Oh,
move that
no problem,
over
Stephen.
by towards B.
So
this-
the
oh, yeah,
section
this
C
is
is
distraction.
Yeah,
That,
yeah.
yeah, so, 525.
All right, so tell me what to write down. BX equals what? Not just the number, what do we write down?
It equals, 725 times,
Put it in terms of B, which is
Okay, yeah.
725, times what?
times 840 over 1160.
840 over 1160. In other words, millimeters over millimeters, right? Yes, so 840 divided by 1160. So what do we get for our magnitude?
525.
Is it 525? So again, they're making the numbers come out nice and round for us. So now we know the components of this 725 Newton force. Let me go ahead and just draw them in. I'm going to get rid of the 725 Newton force, at least, well, I guess I'll put it over here, 725. And guess what? We really don't need those dimensions anymore. They're not really interesting.
I think we need more colors.
I agree. I'll get a blue color when we have a break. 725, this is the 500 Newton side, and this is the 525 Newton side. Okay. So we could also, since we've calculated the magnitude of this 500 Newton force, this one's easy, right? It's a 4-3-5 triangle, so scaling it is pretty trivial. So the vertical component here is, which way is it? 4? So that's 400 newtons. And the horizontal component is 300 newtons. Okay. How about this 780 Newton force? Could we just write down the vertical and horizontal components? How about we write down an equation for the horizontal component of the 780 Newton force based on this triangle you see here? Obviously, all we're doing is scaling the hypotenuse, right? So they're both going to begin with 780 newtons. Okay. Now, of course, this 300 Newton force is negative, but we'll take care of that in just a second. Okay. This one's going to have a negative vertical component. Don't worry about that right now. Let's just get magnitudes. So 780 newtons, the hypotenuse, multiplied by what? Go ahead.
12 over 13.
12 over 13. 12 thirteenths. 12 thirteenths. You see that? That way we get the horizontal component of the hypotenuse, the 780 Newton hypotenuse. How about the other one? Somebody else. 5 thirteenths. It's that simple. See? So now grab your calculators. Let's figure out these magnitudes. The reason this works is because we have forces lying along geometrical directions where we know something about the geometry. Okay.
Your vertical is 300. Oh, yeah, yeah.
300? And they made it come out nice and round, probably did so for the x component.
And the other one is,
That's it. 720?
720?
Yeah.
Now, that's not what they asked for. They asked us to find, let's see, determine the resultant of the three forces exerted at point B. So now we've got all three forces. How would we calculate the resultant? I'm going to go ahead and write down the resultant as a vector from the get-go. Okay? How am I going to do that? Well, all I'm going to do is where I've got a positive component. Well, what do I mean by positive and negative? Well, there's positive and negative, okay? X and Y. What I mean by this is I'm just going to add all of the horizontal components of all the forces. So 720, that's the horizontal component of this, it's in the positive direction, minus 300. Why minus 300? Well, because this 500 Newton force has a negative component in the horizontal direction. How about the 725 Newton cable force? Well, that also has a negative component. I guess it would help to write 300, wouldn't it? Negative component of 525, and these will all be in the I direction. Okay? In other words, in the horizontal direction. On the other hand, for the vertical direction, well, let's see, we've got two forces that are in the negative direction. In fact, it turns out, well, no, it doesn't turn out. I was thinking this has a 300 Newton force. It doesn't. It's 400. So let's see. Let's go in the same order. We had 720 first, so we were grabbing the 780 component. So minus 300 from this force, minus 400 from the 500 Newton force, plus 500 J, and of course, all of these are newtons. Okay. Then to simplify it down, we just do the math. So let's see, this is what? 825 from 720? So that's what? Negative 105, if I'm thinking right? In the I direction. And then that's minus 700 plus 500 is negative 200 in the J direction, newtons. Okay. So there's the resultant vector. Why would we care? Well, because we might need to know what's going on back here at A. As a matter of fact, the force that has to be applied at A is equal and opposite to that for this body to be in equilibrium. And you might say, well, wait a second, I don't know what direction this is, but it's probably got some angle. Well, in fact, we could say both are negative, so it's doing something like that, right? That resultant is acting something like this, and you just said that you need equal and opposite, so it's going to be doing something like this. Isn't that going to cause the whole thing to tend to twist? Yes, but that's a topic for another day. The fact is, we still need this force exerted at point A, which is the only place we can, because that's the only place that's connected to the wall. We've already taken care of the cable. The cable's baked into that, all right, that's done, cable's over. So now we need this magnitude equal and opposite. Notice those two would be parallel. They are what's called a force couple and will tend to cause rotation, but we'll take care of moments a little bit later. Turns out the wall can twist on it also and resist that couple, okay? But we'll deal with that later, like I said. Okay, any questions so far? All right, well, I think that's it for that problem. They just wanted the resultant, so there it is.